There's people on YouTube, waiting eagerly.
Probably routine, no?
Yeah.
I think I'm visible on YouTube as well.
You have you?
Yeah.
That's the intention, right?
Yeah.
No,
Everything's
it's
working
just
though.
Max is sitting where I usually sit.
I can move. You don't have to transfer this giant.
It's way too heavy.
It's a lot
Right.
of effort.
So it's a great pleasure to have Tony again. He was the first speaker of Discrete seminar, I guess. And now he will talk about rainbow cycle conjecture. Please.
Thanks. So it's always a pleasure to be back in Korea. I was a postdoc at Sangil many years ago, and it's really great to see how combinatorics has really grown since I left. So I want to tell you about one of my favorite problems, and in the interest of not putting anyone to sleep, I'm gonna go very slow, and if something is unclear, please just interrupt me and ask questions. Okay, so so the story begins with a quite famous conjecture about digraphs called the Caccetta-Häggkvist conjecture, which maybe most people know, but I'll just write it down, right? So, let's see if I can spell this right. So this is quite an old conjecture about digraphs. Maybe it's the most famous open problem about digraphs, and it's a very simple statement. So it says, so let D be a simple. So I'll tell you what simple means. It's probably not what you think it means. So a simple n-vertex digraph with minimum out degree at least R. So, okay. And then the conclusion is that you should have a short directed cycle, right? So, so then D has a directed cycle of length at most n over r, and you have to take the ceiling. Okay, so this is a very simple statement. Okay, I have to tell you what simple means. Okay, so for simple, actually I don't really care that your digraph has loops, because that's a short directed cycle, right, of length 1. So this is something I allow. I actually don't really care that your digraph has parallel edges if they're in the opposite direction. So this is also okay. But I don't allow you to have parallel edges in the same direction, right? So, so something like this is not allowed. It's an X. And that's the definition of simple, right? So you have to forbid this because this would be a way to force the out degree to be huge without forcing short directed cycles, right? You can just take a thickened Hamiltonian cycle, for example. Okay, so this is the Caccetta-Häggkvist conjecture. It's still open. I will tell you some partial results about it. Many smart people have thought about it, and it's still unsolved. Okay, so when you have a hopelessly hard problem, the thing to do is to think about something that's even harder. So that's what this talk will be about. And so I won't say much more about Caccetta-Häggkvist at this point, except, okay, let me maybe slide this up. And this down. Maybe. Then let me just give an example that shows that, okay, if it's true, then this n over r is just best possible. Okay. So the example is pretty simple. You take your n vertices and you put them, in a circle like this, and then you connect a vertex to, the next r guys in the circle. So maybe if r equals 3, this guy is connected to this guy, and this guy. Right? And so now, in order to make a directed cycle, you need to go like at least n over r steps to get all the way around. Right? So, so if it's true, then this n over r is optimal. Okay. Are there any questions so far? Okay, good. So let me tell you what this rainbow cycle conjecture is, and why it's actually harder than Caccetta-Häggkvist. Okay, maybe I'll just move here. Why not? Okay, so the good thing about Aharoni's rainbow cycle conjecture is it's just about graphs. So we exit the realm of digraphs, which to me, feels easier, at least, where I like thinking about graphs instead of digraphs. And it's just about edge-colored graphs. So there's no directions. So let me tell you what it says. So he made the conjecture around 2017. So let's let G be a simple. So again, I'll tell you what simple means. Simple is a property of edge-colored graphs, so it doesn't mean that the graph is simple, but I'm just matching the adjective we use for digraphs. So let G be a simple, let's say, n-vertex, edge-colored graph. So the key thing about this edge coloring, so it's not necessarily a proper edge coloring, it's just a partition of the edges, and the number of colors has to equal the number of vertices of the graph. Okay, this might seem weird, but we'll see why that's the case. So with n colors, with n color classes of size at least r. Okay. And then the conclusion is that you have a short rainbow cycle. Okay, so then G has a rainbow cycle of length at most the same bound, n over r. Okay, so here rainbow just means you can use at most one edge of each color. Right? Sometimes in extremal combinatorics it means you take one edge of each color, but we want them to be short, so we just don't want any color to appear twice, but obviously not all the colors appear.
Do you assume that color classes are disjoint?
Yes. So it's the color classes are just a partition. It's another way to say that you've just partitioned the edge set into n parts, right? And I should tell you what this simple means. So okay, maybe I'll use this yellow and blue. So I guess I don't really care if you have loops, because a loop is just a rainbow cycle of size 1. Oops, okay, I lost some green. I don't really care if you've got parallel edges, as long as it, you know, the edges are different colors, right? Because that's like a rainbow cycle of length 2. But I do care if these color classes contain parallel edges of the same color, right? So this is not allowed. Okay. And again, you shouldn't allow this because this is a way to make the color classes huge without short rainbow cycles, right? So again, you can just take, you know, a thickened Hamiltonian cycle, right? Okay.
But you can also take disjoint union of monochromatic cliques. That doesn't give you short rainbow cycles.
Disjoint unions of.
Monochromatic cliques. So what do you mean by edge colored?
It's yeah, but you need to have like the number of colors is equal to the number of vertices. So you can't do this, right?
I see.
Okay.
But can you assume that some of the color classes are n?
No, there's like exactly n color classes.
And each color class has size at least r.
Yeah.
Right, that's what.
Oh yeah, it says and this R.
Yeah, sure.
Yeah.
But we'll prove like a defect. Like, so the theorem we prove is actually like a defect version of this, where we allow some color classes to have size less than r. Actually. Okay. Okay. Is the statement clear? Okay. Okay. So now let me at least show you the proof that this conjecture, you know, implies Caccetta-Häggkvist. Right. So the proof is not hard. Let's go. Okay, so maybe I can erase this.
So wait, what did edge color mean?
It's just a partition.
Okay.
That's all. Okay, so that is Caccetta-Häggkvist.
Rainbow means uses distinct colors.
Yeah, so rainbow just means you can't use two edges of the same color. Okay.
And so that blue loop there, that's a rainbow cycle.
That's a rainbow cycle, right? It has just one edge. Okay, I mean, you might think it's a bit silly. I mean, it is a bit silly, this simple
So you
step.
allow the blue loop, but it's not that interesting if your graph has it.
Yeah, then the theorem is just true.
This is.
Yeah, I mean, the simple is a bit silly. The only reason to actually have it is that you kind of want Caccetta-Häggkvist to be true, like, up to out degree, more than n even, right? You just want it to be a statement that's true for all r, and so, like, this is why, right? So, like, so if you allow loops, then you can actually have, like, you know, out degree more than n, actually. Right? The only way you can have out degree more than n is if you have a loop.
Is this for like, so is there some relationship between n and r which is being hidden here?
No?
If r equals n,
Yeah, this is what I'm saying, right?
Oh.
So if r is equal to n, right,
yeah.
then, like, okay, like each, right, so each,
Can't I just have a bunch of Hamilton cycles? How are you
I
gonna get?
mean, you're gonna have at least one loop, right?
yeah.
Why?
Because no parallel edge.
Oh,
No, at least one loop or one.
but he's
cycle.
allowing parallel things from each color, right? Or from different colors, right? Why can't everything be a Hamilton cycle, each color class?
And if you have two parallel edges with different colors, then you have a cycle.
Cycle
That's,
length.
but you need a cycle of length 1.
Cycle. Oh yeah, the cycle of length.
You don't have a cycle of length 1. You've got a cycle of a rainbow cycle of length
Oh,
2.
when n is r is equal to n.
Yeah.
And then in one use the one color class, then each vertex can connect to another vertex n-1, and you can connect with one color to another vertex. So you need loop.
Wait, why didn't you?
I mean,
If the color class is actually n,
Yeah.
I
then
mean,
there's only n-1 different vertices to connect to, right?
No, but that's the directed version. This version.
class is a Hamiltonian.
Yeah, so okay, so
Some
maybe
relationship. I don't know what this is.
okay, so maybe I should say that let's say that I guess in this version it looks like the only thing we need is like R is less than F.
Okay. then I believe that. Now I.
But in this version we don't.
Yeah, this version you don't, as you say, because
Yeah.
there we have this meeting.
What
I
is
see, I see.
size? What is the size? Minimum size in Aharoni conjecture?
These are just like this is the number of edges of
Same
that color, right? So all the color classes have at least R edges. I think once I do the equivalence, it'll all become clearer. Okay, so let me just give the proof. So I'm doing a proof that I guess Aharoni implies Caccetta-Häggkvist, right? Okay, so let's let D be this digraph that satisfies the conditions of Caccetta-Häggkvist, and I'm gonna make like an edge-colored graph out of it that I'll apply like Aharoni's conjecture to, right? So, okay, so I have my digraph. So the digraph looks like, okay, so maybe there's vertex 1, there's vertex 2, there's vertex 3, and there's vertex n, right? And what I can do is I can look at all the arcs that leave vertex 1, all the arcs that leave vertex 2, maybe all the arcs that leave vertex 3, and so forth. Okay. And to make the edge-colored graph, all I'll do is, I'll color these guys like red. I'll color these guys orange. Color these guys yellow. I'll color these guys blue. So I just forget about the orientations of the arcs, and I color an arc according to the label of its head, right? So this is what I'll do, right? And this is why it's important that the number of color classes is equal to the number of vertices of the graph, right? Because in this coloring, every arc received a unique color, and there's like n colors because there's n vertices, right? And then because of this out degree condition, each color class has size at least R, because each of these vertices has out degree at least R. Right? So, and in fact, all the color classes are just stars centered at these vertices, right? But Aharoni doesn't care about that. Aharoni just says, as long as your color classes are large, they have size at least R, you will have a rainbow cycle in any edge-colored graph, right? Okay, and moreover, the definition of simple is chosen so that, since this digraph is simple, this edge-colored graph that I made is also simple. Right? This is why I used the same word, right? Okay, so in this digraph, I will definitely get.
Sorry, I forgot what simple means.
You see these.
Those guys there?
Yeah. So
the first one is forbidden.
just this thing is forbidden, right? So the fact
So
that
each color class induces a simple graph.
yes, well, except for loops or loops.
Except for loops, but loops already solve the problem, so it's
Sure.
okay.
Yeah.
Okay.
So the vertices numbered from 1 to another vertices of the Aharoni's.
Yeah. So it's the graph is just it's the underlying graph where it's the same vertex set and you just forget the orientation of all the arcs, and for the colors you just color according to which vertex I'm the head of. Right. Okay. Right. So I get something that satisfies these conditions, right? So in this, in this edge-colored graph, I'll find like a short rainbow cycle. Maybe it looks like this. Well, how many colors do I have? Okay, white is a color. White is a color. So I've found this rainbow cycle, right, in this edge-colored graph. But now if I go back, right, to the digraph, like this set of arcs, right, must be a directed cycle, right? Because directed cycles are the only things that are actually rainbow, right? So if I'm not a directed cycle, then I will definitely have, right, so you just, right, so if something is not a directed cycle, then there will be some point in which, you know, you have two things that leave, right? And these two things would be the same color, right? Okay, so it should be clear that Aharoni's conjecture implies Caccetta-Häggkvist. So this is the problem I want to talk about for the rest of the talk. So is it clear?
You could even make a weaker conjecture that instead of rainbow cycle, maybe you want to have a properly colored cycle?
Yeah. So we made that conjecture as well. So I'll tell you about it later, but say in the R equals 2 paper, we already made that weaker conjecture. The only thing you really need is a properly edge-colored cycle, right? I mean, if you want to use, like, say, flag algebras, this will not help that much, actually. But yeah, like you don't need it to be rainbow, actually. If you just care about Caccetta-Häggkvist, right? Okay. Good. So maybe. Okay, I promise this will be like the only question I ask the audience, like during the talk, but let's do as a warm-up, the R equals 1 case of Caccetta-Häggkvist, right? So here you just have, this edge-colored graph where you have n color classes, that are non-empty, size at least 1, and so you want a rainbow cycle of length. So n divided by 1 is just 1. So actually, any rainbow cycle is good, right? So okay. So why is that true?
You just pick one edge from each color class, and then there's a cycle.
Yeah, that's right. Right. So so what Samuel said, you just take one edge of each color, and then you just make the easy observation that every n-vertex graph with n edges has a cycle, right? So, I guess, already you can see that maybe, by making things harder, you can find sort of easier proofs, right? So, in the digraph case, probably, if you were to prove this for R equals 1, you might do something like, okay, let's take the longest directive path, right? And you look at the n vertex of that path and it goes back to itself or something, right? So what Samuel said is probably easier than what you would think for the digraph proof. So I want to sort of convince you that in this setting, you might be able to get more with less. Kind of this can happen, right? Okay, I mean this doesn't really happen, but in principle it could, right? So that was the R equals 1 case. Okay, so the next interesting case is R equals 2. So let me write this down because there's a lot of co-authors on this. So maybe I'll just write this as a theorem. Okay, so apologies to all my co-authors, but I think it'll be too long to write their names, but I will say their names. Okay, so this this is a theorem of, Matt DeVos, Matthew Drescher, Daryl Funk, Sebastian Gonzalez Hermosillo, De La Maya, I'll write this as a H, Crystal Guo, or maybe, me, Boyan Mohar, and Amanda Montellano. Okay, so sorry I didn't write out all
What
your
does
names.
comma mean?
There should be no commas, I guess. So
Ah.
just delete that. And so I was visiting Simon Fraser, I think around 2017, and this is where I heard the conjecture. So we proved that, okay, so Aharoni is true for r equals 2. Okay, so we did sort of the first case. And I guess the proof is not really that complicated, but it uses the fact that Caccetta-Häggkvist is true for r equals 2. So it uses Caccetta-Häggkvist as a black box, which, okay, maybe is not that satisfying, but this is what happens. And this is sort of a theme, like, throughout the talk, that I told you that digraphs are scary. So if you do sort of algorithms, we can imagine that anything about digraphs is like NP complete, like it's beyond our capability. So anytime we have to think about digraphs, we'll just use some theorems that other people already proved. And most of the proof will just be, reducing to the digraph case, right? So, okay. And that's what happened in the r equals 2 case. Okay. Okay, so what else is known? I can slide this up. Okay, there's less authors on here, so maybe I can even write them out. Okay, so the next right, so the next open case would be what happens for r equals 3, right? Mm-hmm. And so so there was a workshop in Matrix in Australia in, I guess, right, this is one of the first workshops after the pandemic, so for me it was a great chance to think about this problem because I think it's such a lovely problem. And we proved some things during the workshop. Okay, let me, I guess, just write out like what we proved, right? So maybe I can write it this way, right? So okay, so for r equals 3, so this means this statement with r equals 3, there is a rainbow cycle of length at most. So I think what we're able to prove is 4n over 9 plus 7. So this is a theorem of Katie Clinch, Jackson, Gurner, me, and Freddie Illingworth. And this is kind of what we thought about during the workshop. Okay, so you see that this is not tight, right? Like you would really we want n over 3. So instead we have 4 9s times n, and we have this leftover constant term as well with the 7. But, I guess Matrix has like a journal where you kind of like document everything that you thought about during the workshop. So we wrote up this paper and just sort of put our ideas out into the universe. And we also like wrote sort of a survey of all the other results in this area. And I guess the cool thing is that it was like pretty popular. So on the first week after we put it on the archive, there were like 3 groups of authors that emailed us. This has never happened to any of my other papers. One of them was Aharoni, and yeah, so we got a lot of positive feedback, and I think I'm trying to sell that we need more, survey papers in areas. And so anyway, I want to give credit to my co-authors here because I think we had a lot of good ideas in this paper. And if you want to learn more about the problem, this is sort of the best place to read up on it. So just look up notes on Aharoni's conjecture, and you'll see like what's known about the problem and a lot of nice open problems as well. So if you like these kinds of questions, I recommend that you check this out. Okay, so one of the three people that contacted me after the first week was Patrick Hompe, who was a master's student of Sophie Sperkel, and he had sort of thought about this problem, and together, over email, we kind of we proved something, which I'll write down in about a week or so. Okay, so let me tell you what Patrick and I proved soon. But let me give you some more results. Okay, so let me, I guess, tell you the best result before the result Patrick and I. So, okay, theorem. Okay, so there's a huge constant. So let C equal 10 to the 11th, right? And this theorem says that, okay, Aharoni holds up to multiplicative constant, this C, right? So as long as you, so instead of getting n over r, you can get, C times n over r, where C is this 10 to the 11th, okay, right? So, Ng be a simple n-vertex edge-colored graph right, so with n color classes of size. So before they had size at least r, but let's now say they have size at least C times r, right? So if you increase the color classes to be of size C times r, then G has a rainbow cycle of length at most, n over r. Right. Another way to write this would be, okay, the color classes have size r, and then the C gets multiplied here, right? Okay, so it's off by a multiplicative factor of 10 to the 11th, right? Okay, so let's see this. I should also write who proved this. So this is a result of Hompe and Sperkel. Okay, good. So okay, so now I can tell you what we proved, the main result of this talk. Okay, so this is theorem Hompe. Okay, so for all R at least 1. So basically what we proved is that Aharoni holds up to a fixed additive constant instead of this multiplicative constant, right? So if you fix R, you get n over R plus a constant that depends on R, right? So there exists a constant. So let's call it alpha R. And alpha R is not so big. It's about R to the 5th times log squared R, right? Right, such that if G is a simple n-vertex edge-colored graph, with n color classes, of size at least R, then you have a rainbow cycle of length n over R plus alpha R, right? Cycle of length at most. So n over R, plus this alpha R. So, so instead of having this multiplicative factor, you just get this additive term here.
So, what roughly is hidden in that O?
Oh, the big O?
Yeah.
Yeah, it's about 3 million.
Okay. It's much smaller than something.
Yeah, so this is smaller than this.
Not that it
thing.
matters.
That's right. Yeah. So 3 million is okay. 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 So for the rest of the talk, let me just give you some ideas of the proof. I'm not gonna. It's not that long, but I won't really go through everything. So first of all, let me say that this isn't the real theorem that we prove. So the real theorem that we prove is we actually allow some color classes to have size less than R. That's quite convenient for induction. So you define something called deficiency, and depending on the deficiency, it will add something here. Okay, right. But in the case that we really care about, the deficiency is 0, so it doesn't really matter. Okay, and then let me just tell you, some tools that we use that maybe will be useful for you. So let me go here maybe. I can erase this. Okay, so like in this setting, as kind of Sangyeol's proof showed, you can try to use density. Actually, right? This is something you might not use in the directed setting, but density is something you could try to use where, let's say you take an edge of each color. If you can make some subgraph that has way more colors than vertices, you would kind of be happy, right? So, and this is the theorem that we use to kind of handle this case, right? So this is, let me not misspell these guys as well. So theorem. Okay, so this is a theorem of Bullabosh and Zimmeretti. Aha. I think this is right. Okay. So this is just a theorem about girth of graphs, right? So it's probably a theorem that could be useful. Okay, let me just state it, right? So for all n at least 4 and k at least 2, so every n-vertex excess k, I'll say what this means in a second, graph has girth at most this expression. So I guess 2 times n plus k divided by 3k, and there's a weird term here, log k plus log k plus 4. Okay. So this is just a theorem about graphs, right? And the way that we would like to apply it is to sort of do what Sangil said, right? Like, let's take a transversal that's, so this excess k means that the graph has at least k more edges than vertices, right? So previously we were talking about excess 1 graphs, right? Or sorry, excess 0 graphs, the same number of edges as vertices. Excess 0 graphs already have cycles, right? And then as you increase the excess, this number goes down according to this formula here, right? So it's not really tight for small values of k, right? So for example, for excess 1 graphs, you know, the girth could be around, 2n over 3, right? So the extremal example would be, if you take 3 paths with about, n over 3 vertices on each of these paths, right? So then the girth is about 2n over 3. But, as k gets bigger, they conjecture that, this is close to the answer.
Sorry, but what is the definition of excess?
Yeah, so excess k is a graph that has k more edges than vertices.
So you could write n plus k.
You can.
Okay. N vertices and n plus k.
True. Okay. Okay, so this is a tool that we'll try to use by just taking a transversal, like say 1 edge from each color, that's on like a small number of vertices. Okay. Okay, and then okay, so maybe I should also tell you. Okay, yeah, maybe I should also tell you the theorem of Shen. So remember, we don't want to think about digraphs, right? So we want to use theorems that are known. So let me erase this. Okay, so let's do theorem. So this is all you need to know about digraphs. So it could be that your edge-colored graph is like a digraph in hiding. So we need theorems that deal with this case. So this is the theorem that we'll use, right? So let's let D be. So this is sort of close to Caccetta-Häggkvist. So a simple n-vertex digraph with no sink. So, okay. So then D has a directed cycle of length. So it's at most this quantity. So I guess n plus r plus this deficiency. I'll define this over r, and there's a plus 2r squared. Okay, so this is close to n over r, up to some error term, right? And this deficiency, so in this version, I don't even have like a minimum out degree condition. So I allow you to have vertices of small out degree, but I don't allow you to have vertices with 0 out degree, right? There's this no sink condition. And then this deficiency is just equal to the sum of, say, r minus the out degree of u, right? And so these are u equal vertices with out degree less than r. Okay, right? So some vertices will have out degree less than r, and they'll contribute to this deficiency term, right? So, so for example, you know, like if you have something with out degree r minus 1, it'll contribute to it'll contribute 1 to this term, right? And then you add up the deficiency of each vertex, and you get this quantity here, and it goes up here in this term, right? But when we apply the theorem, our deficiency will be 0. Anyway, because the real theorem that we care about is when all the vertices have out degree at least r, so the deficiency will just be 0. Right?
So is this true for all R? What's the quantifier all R?
This is true for all r. Yeah. So for example, it does prove Caccetta-Häggkvist basically up to an additive constant as well, right? Because when this deficiency term is 0, you just get this sort of additive error, right? So yeah, so it is true that for a fixed r, there is only like a finite number of counterexamples to Caccetta-Häggkvist. Right? This is known, okay? And so for us, the real theorem that we prove also has a deficiency term where we just sum up over the color classes of size less than r. Right? So we allow some color classes to have size less than r, but they just add into this deficiency term as well, right? Okay. How much time do I have? Like,
10 more minutes-ish.
yeah, okay. I'm supposed, okay. Okay, let me continue. Okay, so okay, this is okay. So let me, I guess, just give the proof strategy, right? So we're gonna split the proof up into 2 cases, sort of depending on if the edge-colored graph is close to a digraph or not, right? So let me just quantify this, right? So so let's say a color class is a star color class if, you know, its edges, you know, are a star. Right, so, and in Aharoni, you actually could have star color classes that are centered at the same vertex. Actually, right, this could happen that you have multiple star color classes centered at the same vertex, right? So the proof is going to be a case distinction on the number of non-star color classes, right? So, okay, so basically these star color classes maybe look like this. So you have, you know, maybe the yellow colors are a star, and maybe the red guys are a star. There could be another star color class here. That's it, right? And then you've got another color class, which is a star, centered there. And so these guys are all the star color classes. Okay? And then you have the vertices, which are not the center of any star, right? So, so we call these non-star vertices, right? So it just means that for these guys, okay, maybe I'll draw this as well. Do I have another color? We'll use white. So these guys are not the center of any star color class, right? So we just break up the vertices according to like if you are the center of some star color class and if you aren't, right? And the proof breaks it up into like, do you have many of these guys or a few of these guys? Okay, right? So, so you can imagine that if you don't have many of these guys, then you're like close to a digraph actually, right? And what you would want to do is just think of this as a digraph with kind of small deficiency, right? So you undo the proof that I did before and turn this into like a digraph, for example. So you could orient these edges to go out, for example. And you've made a digraph that almost satisfies Shen's theorem, right? Except for the fact that these guys like don't have any out degree, actually, unfortunately, right? So we actually cannot even apply Shen's theorem directly here, right? Because these vertices are sinks actually in this orientation. So you have to do a little bit more actually, right? So, so you will apply Shen's theorem in some auxiliary graph, which I won't tell you what it is, but you can imagine that actually even if you have just one of these guys left over, it's unclear what you should do, right? Because this guy has 0 out degree, actually, right? But it turns out that there is a way to apply Shen's theorem in the case with a few non-star vertices, okay? And then the other case is if you have lots of these non-star vertices. And lots is just a fixed function of R, okay, right? So, you have just some sharp threshold of more than, let's say, G of R or less than G of R, right? And then this, I guess, breaks up into 2 subcases. One is where you can just apply Boulebar-Simoretti in the stupidest way, right? So it turns out that if you have like lots of these guys, then you can make a transversal that just has lots of isolated vertices. This is completely stupid just by counting, right? So the XSK graph that we find will just be something that has many isolated vertices, right? So it turns out that if you have many of these guys, you can actually pick a transversal where you isolate a lot of vertices, right? So these isolated vertices will give you the excess that you need. Okay. And then there's another case where if that doesn't happen, then you have like a rainbow star, actually a fairly large rainbow star, and that's also good for you, right? If you have a fairly large rainbow star, then essentially you can contract it and apply induction. Okay, so, but the moral is that, you know, the case that you have lots of these, you want to apply Goldwash-Simonetti because you have density, and the case where you just have a few of these, you just use a digraph theorem in a clever way, right? So in that case, you're quite close to a digraph with low deficiency. Okay. So maybe that's all I'll say about the proof, but I have time for some open problems. Okay. Let me go here. So again, like if you're interested, there's lots of open problems in that survey article that I listed, but I'll just mention a few of them here. So, open questions. So the nice thing, I guess, about Aharoni's conjecture is that we've gotten rid of the direction, the directed arcs. So it makes sense in like any setting where cycles make sense, right? So everyone here just loves matroids, right? So there are matroid analogs of these questions because matroids have cycles. So matroids, right? And you have to be a bit careful, right? Because right, so if say you take a uniform matroid, then it's not going to have any short cycles at all, right? But it could be true that, you know, if your matroid is, you know, binary or maybe regular, that Aharoni's conjecture could hold exactly even. I mean, I don't know a counterexample for that. Right, so there is an underlying like extremal function here, right? So let's maybe let f n t r equal like I guess the maximum rainbow girth over, you know, all n-vertex, or let's say all simple n-vertex edge-colored graphs with, say, t-color classes size at least r, right? So when I write it this way, it's quite unnatural that like the number of colors is equal to the number of vertices, right? So you know, Aharoni basically says that, you know, f n comma n of r is like n over r, but there's no reason to restrict to the case that the number of colors is equal to the number of vertices, right? So many extremal questions you can actually phrase as like, what is the value of this extremal function here? And yeah, so people have thought about you know, this function, right? There's more, but okay, maybe I'll just stop in the interest of time. So thank you.
Thank you. Any questions?
About oriented matrix.
Oriented matroids? Yes.
I mean, that's the generalization of a diagram, right?
I mean, I'm scared of digraphs, so I'm more scared of oriented matroids. But yeah, this makes sense. Yeah, I would say. Yeah.
What about bipartite with perfect matchings? I mean, that's the generalization of a digraph. I'm serious. Like the advantage could be you could relax the problem and switch to perfect matching. So if you fix the perfect matching, you would have one digraph. If you switch it, you might get an easier problem. I'm just asking if anybody considered this.
Yeah, I'm not sure. Yeah, I'm not sure. I guess what I will say is that, yeah, I guess Aharoni spoke at IBS before about, like the structure of color classes where, I guess the furthest you could be from like a star is if you have a matching of size 2, let's say. Right, so if you're not a star, you have a matching of size 2, or you're a triangle. Right. And then it turns out that in that case you get much better than n/2. So for example, if every color class has a matching of size 2, you actually have log n rainbow curves. So
That's not exactly.
this is not what you're saying
Yeah.
at all, but it's something. I know what you're saying. I don't know the answer to your question. Yep.
So did you look at whether your technique can say anything to this function when t is not equal to n?
Yeah, there's some results. So at some point, like even in the R equals 2 paper, we have some results where, once the number of colors is too small, then the rainbow growth becomes infinite, like clearly. And then there are results where this t is bumped up a bit, and then you get improvements actually, right? So I think it's interesting to see this dependence actually, right? So there are results. They're in the survey article. So
And just so that I don't have to look it up later. So if you just look at a normal graph, we look at a normal graph and has high degree, we get short cycles, right? So if I just remove the fact that it's directed, I'll get this.
you had a question?
Is there some version of Aharoni's conjecture for hypergraphs?
For hypergraphs. This I'm not sure. But yeah, I mean there should be, right? There's different notions, right, of cycles in hypergraphs, but yeah, something like this. That's not in the survey article, but something like this should be known.
What about the other extreme where R is big, like n/3 or n/2?
Yeah. So, right. So I guess a lot of people have thought about the n/3 case of Caccetta-Häggkvist, right? So, right. So it says if you have out degree n/3, you should have a directed triangle. I guess the best proof of that uses flag algebras. It's one of the success stories of flag algebras. There is a flag algebra proof. So, okay. So you get something like, okay, if you have 0.345 n, then you get a directed triangle. They did that with flag algebras for this problem as well, and it's a bit worse than so 0.37 something, right? Let's say. And then, yeah, actually I was thinking, okay, so I should say that I've been thinking about this a bit with Bruce Reed, because I stayed in Taiwan after the workshop, and Bruce had a lot of good ideas, so I don't want to announce anything, but we definitely proved something, right? And yeah, so and more in the dense regime, actually. So, yeah.
Any other questions? No.
Is there any approach using geometry? I mean, there is well-known.
Yeah, there are, I guess, topological methods, right, to get rainbow things, but this I don't know. But yeah, it's worth thinking about.
Right, if there's no further questions, let's thank the speaker.